It's actually because I forgot to put my watch on before bed, which is my alarm. But cool. All right, chapter 2. Here we go. Over the next several weeks, we will be looking at polynomial, and rational functions. Now, with this, I kind of alluded to the fact that we're going to be talking about quadratics as well, but quadratics are polynomial functions. So are cubics in 4th degree and 5th degree and 6th degree. We won't graph 5th and 6th degree functions. Those are awful. But we'll be looking at it. So for today, to jump in, we're going to look at 2.1, and our focus is going to be on quadratic functions and models. Okay, before we just say let's talk about quadratics have typically more than one term. Now the parent function has exactly one, right? It's x squared. But give me another few examples of something that could be quadratic, maybe more complex than x squared. Okay, chat with your neighbors, everybody, every team, pair, however, come up with 2 examples of quadratics other than just y equals x squared. We're all examples of quadratics, right? The largest power of x that we can have is an x squared. We're not allowed to have any x's in the denominator, anything like that. We have nice powers. So if we have an x to the second, that's the biggest one, we're never going to have an x to the 1.5. Now, x to the 1.5 does exist. It's something else. You would call it 3 halves. But we have nice integer powers. What we are really alluding to, or what I'm alluding to, is that quadratics, in all reality, are just a special type of, and we're going to define this, a special type of a polynomial function. Now, in Algebra 1, you guys spoke about monomials and all that good stuff, and it most commonly comes with when you're learning how to simplify ugly fractions. You learn how the x's divide out and things like that. Those are monomials, and then you start building it up, right? So instead of just x over 2, you get x plus 1 over 2. And we start seeing that, hey, there's ways to bust those things up as well. Rules get a little bit more complex. We're about to write what is certainly going to be the ugliest thing you've seen in this class so far this year. It might be the ugliest thing that you see all year. Here's the deal. It just looks ugly. What we're going to write down, it looks awful. It's not, and we're going to make sense of it. So, by definition, we're going to sneak a couple things in here. We are going to say that for a polynomial function, we will first let a couple things be true. The first of these is I'm going to write let n be in this terrible thing, and I want you guys to tell me what this means.
Integers.
What kind of integers? So the z is the integers. What about the plus? Positive integers. Give me some examples of positive integers. 2, 3, 4, 5. It's really just the natural numbers. Okay, so we let n be a positive integer, and we're going to get some subscript stuff going. Let's say we have a sub n, a sub, what's one term before n?
N minus 1.
Good. A sub n minus 2 would be the next, right? And dot, 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 all the way down to eventually we get to a sub 1 and a sub 0. Now, nobody knows how long this list is right now because I haven't told you anything about n. If n is 12, maybe this thing has 13 numbers. Now, the 13 comes from this very last a sub 0, which is weird that we do it. But just like if n is 2, we have a quadratic, and you can write at most a quadratic, which is an x squared, has 3 terms, right? There's that extra that we just highlighted here. Okay, everybody okay with these are just numbers? Now, what if I say all of these guys are this? What did I just say they are? All of these numbers that we wrote are real numbers. Okay, that's it. Then, as long as, if a sub n, that very first number, as long as it's not 0, that's the only requirement. Then, if that all is true, then the function I'm going to say the polynomial function. Is it a stretch to use poly for polynomial? So everybody okay with that? Is written, and here is the ugliest thing I legitimately think we'll do all year long. Okay, here we go. Any polynomial can be written, as long as all this is true, as follows. F of x is equal to a sub n, x to the n. Now, if this were quadratic, there's just some term or coefficient that goes on the x to the 2, right? And then we would write the next smallest power. And if it were quadratic, it'd be x squared and then x, right? But what if it was x to the n? So maybe it's a cubic or a fifth or a 12th, don't care. My next term is always 1 degree less. I will say it has this coefficient, the number in front of the variable, and x to what power? Good. N minus 1. Plus, I'll do one more here. Let's say that now we're at the a sub n minus 2, and we're going to have x to the power of n minus 2. Now, depending on how big this list is, it could go a really, really long time, right? Like if I were writing something that started with x to the billion, cool, I have 1 billion and 1 terms to write down. That's a lot. Eventually, though, if I start at x cubed, I just want to think what happens at the end. I go something x to the third, plus something x to the second, plus something x to the first, and then eventually plus something x to the 0. Now, we never write x to the 0, ever, because anything to the 0 is always what? Not 0, that's not true. 1. So whatever this term is, I don't even have to put the x to the 0 on it. There should be an x right here, now that I'm looking at it, on the A1. Just, put an x right here after it. This thing could be x to the 0, but that's just 1, so it's just a number. Now, eventually, we will get down to this, a sub 1 x, and we'll end with some constant. And I'm going to sneak in, if you didn't catch it, I forgot an x right there. Do you guys agree that this is ugly?
Yeah.
It looks kind of awful. It's not. And I'm going to show you and convince you, I think, really quickly. So in quadratics, in polynomials, if, and I'm not even going to write this down, what do we call it if the biggest power of n that we've chosen here is a 2? So that it was something x squared plus something x plus just a constant in the end. What side of function looks like x squared plus something x plus a number? Quadratic. So, quadratic functions live within my polynomials. And it's easy to see, and we'll just make sure we can identify that this is ugly, but it's not. So here we go. We're just going to look at this. F of x equals, I don't know, 3x to the 5th, plus, 3x squared, plus 5x minus 1. Is this a quadratic?
Yes.
Okay, you know that even without me writing this other stuff, right? Is it a polynomial function?
Yes.
Now, you might know that because I told you a second ago that all quadratics are. Can you link this up with this?
Yeah.
What is a sub n for this?
2.
It's not 2. Check it out. I think that you answered the n question, right? The highest degree is 2. A sub n is just the coefficient of the nth degree. So if this is a quadratic, the biggest one is x squared, right?
Yeah.
So what's connected to the x squared?
1.
There's my a sub n. It's 3.
Oh.
What is, like if we go 1 power down, instead of 2, it's now 2 minus 1, yeah? So what's the term a sub n minus 1, or whatever's connected to the x term? 5? What's this? A sub, it's not a sub 1. A sub 2, a sub 1, a sub 0. If we wanted to, and we don't, but we could I write this if I wanted to be super duper clear? Could I add those? Is this still the same expression if I add that?
Yes.
It is, right? Because x to the 0 is 1, so this just winds up being 1 still, and 5x is just 5x to the first power. These are polynomials, every single one of them. Every quadratic ever fits in here. Now, if I tried to do this, and I'm just going to do a different one, and it's up to you if you want to write this one, but I'm going to show one that breaks. So I'm going to cross it out, just be aware. What if I do 0x squared plus 5x plus 2? Is that a quadratic? Why not?
Because it's multiplied by 0.
Because that first term is 0, which means if I don't write it, when I cover it up, it's very clearly not a quadratic. It's just a linear, right? This is still a polynomial, but it's not a quadratic. Yep, a sub n cannot be 0. Not quadratic. Okay. In general, there's a few different ways that we can write quadratics. And I think that today we'll probably have a lot of talking rather than this. Have you guys spent a ton of time on quadratic stuff in your math career?
Yeah. Okay, so the 3x squared is the a sub n, 5x is a sub 1, and then what's the negative one?
So when we say a sub n, I'm only trying to match it. Do you agree that in this particular problem, n is 2?
Yes.
So I would say that this term, if we're, and I'm just trying to make sense of this, we don't normally see it, but this is like my a sub 2 term. Now I called it n just to make sure that whatever this is matches. So this would be my a, this is x to the 1, right?
Yes.
So this is a sub 1 because those have to match. And if this were x to the 0, we would think of this negative 1 as being a sub 0. Okay. Yep. Cool. All right. True or false, you guys did a ton of stuff with quadratics.
True.
Yeah.
Follow up. If I'm speaking something that doesn't click, you're going to tell me you want me to write it down. Okay, deal. Okay, there is one more thing that I want you to write down. In the most general sense, the general form of a quadratic is something we've all seen. General form. Now, later we will see that there's another form called the standard form or the graphing form. This is the one that's most common. Before you write it down, anybody annoyed by my quadratic that I'm writing here? Why? It's not first. Is it still quadratic though?
Yeah.
Yeah, and it's just ugly, right? It feels unnatural because we never write it that way. It feels so weird because you've learned to write these things in general form all the time. And I know for a fact that you guys use the same letters because I heard us talk about them yesterday. So all we have to do is we'll say let A, B, C. These are 3 numbers that are in the real numbers. And we'll just require that A cannot be 0. If we want the general form of a quadratic function, we are going to use A, B, and C, and I know that you guys use them with factoring stuff. Every quadratic in general form can be written as ax squared plus bx plus c. This is the way that we normally see quadratics written. The way that when I asked you guys to give me some, you all gave me versions of this. Everybody cool with that? Okay, so we have a few things that we need to chat about. And if I need to write it down, you're going to tell me.
Okay.
What's the shape of a quadratic? Okay, so I was expecting everybody to shout out parabola. Half you guys are doing the YMCA dance. I'm cool with it. Is that a parabola?
Yeah.
You might do it here. Can you do it like this?
Yeah.
What determines if it goes up or down?
Negative.
What would be negative, A, B, or C?
A.
Okay, if A is negative, it goes downward. Do these things have symmetry? Is it always across an axis? Like what I mean by that, like if it's centered at the origin, it's an even function at that point because the line of symmetry is exactly the y-axis. But if I shift it over, is there still symmetry on my graph? It's just not on the axis anymore. Where does the line of symmetry always run through? What's that word at the bottom or the top of your parabola? The vertex. Everybody remember talking about the vertex, the lowest or the highest point. Okay, I don't want to graph that one then. Now, when we graph in here, there's a couple ways that we can do it. To start us off, I'm going to claim we only need 3 points, with the understanding that there's truly 5, and we'll talk about why that is. We are going to, instead of looking at graphing from general form, which you can do, there's ways to do it, we'll cover it later, I want to actually get into graphing some of these. So our main idea starting is just polynomials. We'll be talking about polynomials all chapter. Then we're going to zone in on quadratics, but I want to make it much more specific. So let's talk about how do we actually go about graphing quadratics. Okay, I would like to not give you homework this weekend. That's the goal. I'm not going to give you homework this weekend. I can just say that. All right. So, here we go. we are going to use, for graphing quadratics, we could try to find the vertex in that ugly general form, and it would work. Or we can do this using what is known as standard form. Now, if I don't write of a quadratic, is it implied, based on the way that we're writing our notes, that this is a standard form of a quadratic? If you want to write it, please do. If you really agree that we don't need it, don't write it. Standard form of a quadratic. There's another name for this that I don't know how you guys saw it last year, but I'm going to leave space in case we want that other name. Here it is. We like, and I like, and you will like, to write quadratics in this form. Instead of being ax squared plus bx plus c, it is much nicer if we can somehow transition it to look like this. Now, this is so convenient, and I think I heard Karina say she likes this one. Everybody should like this one. If you don't, you will, because if you didn't like it when it didn't make sense, sure, I get that. Anything I should say about HK? Is the what?
No vertex.
Vertex. Is that what you were whispering there, Red? What did you actually say? Okay. I'm okay with that. You're thinking circles. Center of a parabola is a hard thing to think about, but I think that I agree. Okay. HK is the vertex. Cool. It is super duper easy to graph these. What's not quite as easy, but it's still pretty easy, is how do we write them in this form? So, to go, to move, or change from general to standard, we complete the square. Okay, based on the tonal projections that you guys had when I wrote this, all the right? Like not really a word, but the understanding. These were okay to graph for you guys. Do you remember if I give you something ax squared plus bx plus c, how we change it here? And that's okay. We're going to review this whole process of completing the square. It is a technique that you can use to factor stuff. If you guys derived the quadratic formula last year to see where the quadratic formula actually comes from, you did it with this. That's how you do that proof or that derivation. So let's jump right in. I'm going to annotate like crazy. I want us for this example, and we'll do a few of them, but I want to write in standard form. And I'm just going to shorthand STND for standard. I want us to write it in standard form and sketch the graph after the fact. Cool. The sketching, we'll still make a table, but it's crazy easy. So let's dive in. We're going to do an ugly one together, and then I'll have you guys do an ugly one with your neighbors. So here we go. On our very first quadratic, I want us to consider the quadratic that's generated by f of x equals, and we have 3x squared minus 6x plus 4. And what's really weird right now, not weird per se, but I remember doing something very similar with you guys when we wrote the equations of circles in geometry a couple years ago. You probably don't remember how to do it, but we did exactly the math that we're about to do here. All right. Well, if you look at the standard form, a, the coefficient on x squared, did it go inside or outside the parentheses? Now I'm asking you to look at your notes rather than the board, because I've hit. A went outside, right? So inside your parentheses, you had to factor something, because I can tell x minus something squared. What's the coefficient on the x inside your parentheses?
1.
It is a 1. Everybody agree that we don't write it, but there's a 1 right here. We never write it, but it's there. Unfortunately, the a is connected to this. Could we factor it out?
Yeah.
Now, here's the weirder part. I can factor 3 out of anything that I want, and it just gets fractioning ugly. But the 4 is the issue, right?
Yeah.
So we are going to annotate this and try to be really specific. But right off the bat, the first thing that I think is I want this 3 to not be connected directly to this anymore. Okay, I'm only going to factor out from a couple of things. I'm going to factor the leading coefficient. And are you guys do you remember the word coefficient? A number on a variable. The leading is just a 1 on the x squared. Factor the leading coefficient from x terms. Only the terms that have x. I'm not even going to look at the 4 other than to make sure I write down a 4 on my next line. What's up? Absolutely, and I'll show you 100%. I'll convince you that we can do this. Let's factor a 3 out of these. If you factor the 3 out of x squared, what does it leave?
X squared.
Okay, and if you factor the 3 out of this, what does it leave? Okay, so Christina asked a good question. She said, we can do that, and it feels weird, but if we distributed, do we still get 3x squared minus 6x plus 4?
Yeah.
Yep, we can absolutely do that. Yes, sir.
Why don't we take out the x?
Because good question. Red's question was, why don't we take out the x? We are going to make this inside of our parentheses into a perfect square trinomial that can factor as x minus something squared. Like, this is what we're doing. That's a great question. Now, in geometry when we did this, and I tried to do it here, but then I'm going to make it 2 steps. Is everybody okay first before I continue on? Okay, I'm going to rewrite this exact line, and I'm going to leave a really awkward gap after this 2x. X squared minus 2x plus 4. It's awkward, it's ugly, we're going to put something in here. Here's the big question though. I want to have some more stuff in my problem, but I don't really want to change it, right? Because I don't have an equation that I can add the same thing to both sides right now. What's the only number that I can add that doesn't change stuff?
0.
Now I could just write plus 0, but that wouldn't do it. Could I write plus 1 and minus 1? Or plus 5 and minus 5?
Oh my gosh, I remember this.
Now, like in my class you do? Or from last year?
Oh,
Or both,
I
maybe.
remember it.
All right. I know that I use the phrase awkward gap the whole time. Here's what I want to do. Did you guys factor last year with factor tiles?
No. What?
Do you know anything that I'm talking about that? Because you guys say no, but as soon as I draw this, you're going to say, okay, yeah, we did. This, I think, can represent an x squared. This is x by x, right?
Yeah.
Everybody okay if I call that x squared?
Yeah.
Okay, and right now I have 2 x's, and they're negative, so I'll make them blue instead. Do you agree that if I said that this is a 1 right here, that this is a x? Because the dimensions of this would be 1 by x.
Box. Yeah.
You guys call this the box method?
Yeah.
Okay, so it's the area method, all the same. But okay. Right now I have exactly x squared in red, that's a positive, and then minus 2 x's. Everybody okay that that is this expression here?
Yeah.
Is it a square right now? No. Can you guys tell me that, like, can you very clearly see the part of that shape that I need to add in to make it a square?
Yeah.
Okay, just to make sure. Is everybody agreeing that it's this?
Yes.
So let's think about the dimensions of what this would be. I know that this is x by x, and this is x by 1, and this is x by 1 as well. What are the dimensions of this square?
1.
I need to add a 1. But I can't just add a 1 because that changes stuff. Now the question becomes, how do we come up with that here? This one is ugly, it's hard to word, and it's just gross. I wish there were a way around it. But check this out. It turns out that if we want to figure out what we need to add without drawing this picture every time, if we take this term, I'm going to change here. We're going to add and subtract. And I need to pause here because the letters stuff gets weird with it. We started with this as ax squared plus bx plus c, right? Can we pretend, and not even pretend, but when we just look inside the parentheses, do you agree that we've changed a to 1 inside?
Yes.
And b is now what? So check this out. If we add and subtract b over 2 squared inside of my parentheses. You guys told me just a moment ago that I needed to add a 1 here. Let's just see what happens. What is the b term here? Negative 2 and divide it by 2.
Negative 1.
Square it.
1.
Is that what we just said we had to add?
Yes.
Okay. I have cheated right now. Not yet. I mean, currently if I stop here, I've cheated. What did I do wrong?
You have to subtract it.
I need to subtract it as well. I need to add a 0. I have changed fundamentally the way that this looks, but I haven't really changed it. I just added 0 to it. Everybody good?
Yeah.
Okay. One of these isn't nice. When I added the 1 in here, when we did that b over 2 squared, it was a positive 1, right? But I also have a negative 1. I don't want this in here anymore. Now, that whole parentheses, we use those parentheses to indicate everything in here would have to multiply by what to get rid of them?
3.
Now, I could distribute it to all of them. Could I also just distribute it to one of them?
Yes.
Yeah. We are now going to our next step, and I'm going to make sure that there's like a clear separation here. We
I
are,
remember this.
I don't like the way that looks. I'll fix that. We are going to distribute
I remember something similar. Very similar.
and remove only the negative that we just introduced. The negative we introduced. That leaves us with a 3, and I still have x squared minus 2x plus 1, and I close my parentheses. People try to get goofed up and write a minus 1 out here.
No, it's -3.
It's a 3. We've really added 0 of the form plus 3 minus 3 if we had distributed. Now, to remove it, I will distribute just to the negative, and I'm going to take a what out of it? A negative 3 plus 4. This is my distribution to that same negative value. Okay. We are at a really nice spot to pause. I wish that we were like 2 minutes ahead of where we're at, but this is an okay spot to pause. This weekend, I'm not going to give you homework, which means tomorrow I'm hopeful to see you guys all at the race cheering people on. Sunday, I hope to hear you from your houses cheering for the Cowboys. And I will see you cool cats and kittens on Monday.